Hello, I'm Hugh Manfield and welcome back to my science channel. Now today is another episode of What Einstein Got Wrong, but we'll actually be talking about how to make Einstein right. In fact, we're talking about a special theory of relativity, which is almost perfect, as I've said in some of my comments before. So let's take a look at Einstein's thinking as he developed special relativity. Now, Einstein would consider only material bodies. He would not attach any significance to anything having to do with empty space. And this goes back to his classical upbringing and the philosophies of the time, which regarded the void as nothingness, which would have no physical properties. And this is consistent with some of the Renaissance philosophers, and it goes all the way back to some of the ancient Greeks. What special relativity did, which was different at the time, it departed from the Newtonian classical concept, which is actually great for Einstein to have departed from his classical roots in such a dramatic way. He said, space and time are not separate things, they're related, and as an object travels faster and faster, closer to the speed of light, it's going to become length contracted and time dilated. We use the Lorentz transform to tell us, based on the speed, just how much length contraction and time dilation there's going to be. So that's special relativity. Now, to understand why this was significant, we have to look at the timeline of Albert Einstein's life. And it gives us some insights into why he thought the way that he did. Well, first of all, he was born just before 1879, and during his youth, there was a famous experiment conducted called the Michelson-Morley experiment. They were trying to find the speed of the Earth through the ether, and they thought they could do it by measuring light coming from one direction and then light coming from another direction. And if the Earth is moving through this medium, there ought to be a difference between the speed of a light coming from one direction or the other. And what they found is that there's no difference. It doesn't matter the time of year, it doesn't matter the time of day. Anytime you measure light, it's always traveling at the same speed, no matter which direction it's coming from. And this was very puzzling from the Galilean point of view and the Newtonian point of view. And Einstein solved that with special relativity in 1905. And I believe that's when he was doing some of his best work. Shortly later, Minkowski, based on special relativity, developed what's known as Minkowski space. And Minkowski space is one of the key foundations of fluid space theory, and I can go into that later. But if you look at what was known at the time, it was still 6 or 7 years before Rutherford discovered that atoms weren't solid, uniformly dense objects, that they actually had a tiny core, and most of the mass was concentrated at the small central core of the atom. And then shortly after that, the Bohr atom was discovered. So this is maybe a decade after Einstein developed special relativity. So Einstein's thinking during the development of special relativity was based on the classical concept of spherical atoms of uniform density, this idea of matter that was suddenly shown to be incorrect. Now, I don't know about you, but if you're like me, when I read a new paper with a new discovery, I think, well, let's see if it passes the test of time. And Einstein probably maybe had the same thought. He was going to wait and see. In the meantime, he was developing general relativity. And shortly after publishing general relativity, he got a letter from Friedman who said, you know, your math leads to an expanding space-time. Around 1917, Einstein introduced the cosmological constant. Now, let me say something about the cosmological constant. Einstein calls it a constant because he was trying to create a static cosmology. And if you look at the timeline, galaxies weren't even discovered for 20 years after special relativity. So in Einstein's world, we were in an island universe composed of a dense cluster of stars with decreasing density with distance. And that was thought to be a static situation that was going on forever. Einstein's classical education was of this steady state universe. So he introduced a cosmological constant, and he called it a constant because in a steady state universe it would be a constant. But I take issue with people trying to keep it a constant just because Einstein said so before he even knew about the existence of other galaxies. I mean, do you really believe that at the Big Bang the vacuum energy was at its present level? Do you believe that the vacuum energy of the universe hasn't changed since the Big Bang? No, it's not a constant. Obviously not a constant. We shouldn't treat it as a constant. But that's actually a subject for another video. Let's take a look at Einstein's thinking in regards to special relativity. And today we're going to have Ricky hauling some cargo in her spaceship. And she's going to load it at rest relative to the docks. And then she's going to fly up to a significant value of the speed of light. And we'll see what happens. So, her first cargo is an elephant, and when she gets up near the speed of light, the elephant becomes length contracted and time dilated. Next, she hauls a Formula One race car, and when the Formula One race car gets up near the speed of light, it becomes length contracted and time dilated. And next, she hauls a school of piranha, and when she gets up near the speed of light, the school of piranha becomes length contracted and time dilated. So look at what's happening here. It doesn't matter which random object we choose to put in the cargo hold of Ricky's ship. Whatever it is, it's going to become length contracted and time dilated. So this is starting to sound like it's not a property of the object, but a property of the space when you're moving fast. Let's suppose we put a galaxy into the cargo hold, if you could do that. And we bring that galaxy up near the speed of light. The galaxy, composed of all the planets and solar systems all orbiting, and binary stars and magnetic fields and gas clouds, all of that will become length contracted and time dilated. In fact, there's a recent paper out that as we look out toward the edge of the universe, we actually see, as we should, the galaxies at great distance are time dilated. And since the current theory says that they're moving away from us, they would be length contracted, but we wouldn't be able to see that length contraction because it's along the direction that we're looking. So let's suppose that the cargo hold is empty and she gets up near the speed of light. Won't the empty space of the cargo hold be length contracted and time dilated? And this is where I departed from Einstein in developing fluid space theory. It's not a property of the object, it's the property of the space that the object occupies. And you have to start thinking of space as something real and tangible and depart from Einstein's space denial philosophy. It's time to rethink special relativity and apply it not to the objects but to the space that they occupy. We should accept that an empty reference frame can have significance. So let's say we have Stan over here floating, and he's the stationary object, the rest reference frame in this thought experiment. And Ricky is accelerating past in her ship, and as she goes, she periodically drops a beach ball or some kind of object. So we end up with a string of objects that she dropped, and each one is moving faster than the last because the ship is accelerating as it goes. So you get the string of objects and they're slowly spreading out, and Stan can plot the progress of each of those objects by placing a coordinate system on each object, and each object is going to have its own inertial reference frame. And this goes along with Einstein's way of thinking. But what about the spaces in between? She could have dropped an object there, or here, or there, and that inertial reference frame would then be moving at some speed somewhere in between. In fact, it's possible to think of an infinite number of possible reference frames between each of these objects. But these reference frames won't have a material body in them. But does that mean that they're not significant? There's a potential for an object to be in any of those reference frames, moving at any velocity between any of the actually dropped objects. And this is where fluid space theory embraces the concept of space-time as a real and tangible thing. In fact, if you take a four-dimensional space-time, Minkowski space, you must consider that there's a potential reference frame for any object moving in any direction at any allowed velocity from 0 to the speed of light. And all of these potential reference frames must overlap each other. And they can do so without conflict. And this gives us an idea of space-time where anything is potentially possible and we only observe the actual reality of it when an object or a photon or some material thing occupies that potential reference frame. And this is starting to sound like something that is more in line with quantum field theory. So if you think of a two-dimensional space-time and we add a third dimension, so we can stack an infinite number of layers above and below this two-dimensional plane, and they can all exist simultaneously, and they can contain objects that we can project onto this plane. There can be an infinite number of objects that could be potentially projected onto this plane, and they could all exist simultaneously. That's the same thing that I'm doing in fluid space theory with the four-dimensional space-time. So let's take a look at the solar system. I'm not sure if you can see the orbits of the planet in blue. They kind of fade into the space. But the sun is at the center, and we use the sun-centered reference frame to navigate all of our spacecraft. And NASA does a great job at getting them accurately to all the distant destinations. But really, the space of the solar system is largely empty. Now, since there's nothing in it, does that mean that it doesn't have significance? I mean, if we're trying to transit a spacecraft between Jupiter and Uranus, we still have to cross all that empty space, and it could take months or years to do that. So, just because space is empty doesn't mean it doesn't exist. I mean, if it was absolutely nothing, it seems like we would be able to just jump over it, or it would collapse in on itself. So space really has to be considered as a tangible thing. So to fix special relativity, we simply just take Einstein's space denial philosophy away and apply the Lorentz transforms not only to material bodies in motion, but possibly to potentially empty reference frames in motion. So some of Einstein's best work is still relevant today, but it needs a little update, and that update is simply to apply special relativity to space rather than objects. And that will bring his theory of 1905 up to date. So until next time, I'm Hugh Manfield.